in the bulletin, in the email, the title is more conservative. Now, since we're talking, and I can make it bolder claim. Now, all non-Hermitian systems are PT symmetric with unbroken PT symmetry. Well, of course, there are constraints. Here, all means we only test the finite dimensional. And there may be diagonalizability constraints, but I will come to that. Okay, this is the collaboration work with my colleague, Professor Gong Jianbin, and also his postdoc. Now it's a former postdoc, Zhang Dajian, is a professor in China now. Mainly the talk has 3 parts. One is I will introduce the terminology I trying to use all the previous work, and then I will try to present a new framework. And as a application, I will apply it on Aharonov Anandan AA phase. And I will conclude, if there are questions rise, I can give more technical details in appendices. There are several appendices. Okay, for the first part, I will briefly go through 3 types of system, or actually 2 categories. One is generic non-Hermitian quantum mechanics, which is before PT or during PT, but people didn't use PT language. It's just taking a non-Hermitian system, non-unitary, and what kind of system they describe. Second category is PT symmetric, and I put 2 subcategories here. One is time independent, like Carl Banda and Boycher's potential. And also, I will also discuss time-dependent PT symmetric system, which I mostly focus on. Here is roughly textbook non-Hermitian quantum mechanics. Usually, what they do here, non-Hermitian simply means if you take a naive Dirac conjugate, transpose plus complex conjugate, they don't equal to each other. I will call that non-Hermitian. Whether there's a hidden symmetry, and it's not in the discussion for now. If we have a Schrodinger equation satisfied by this, which is governed by this non-Hermitian Hamiltonian, and then it's easy to construct a bi-orthonormal basis. Basically, we want to recover unitarity. By itself, the non-Hermitian system psi states or the cat states do not satisfy the unitarity. But we can introduce the left state, which evolution is under the conjugate of Hamiltonian. In that case, the left and the right state together show a apparent unitarity, which is a constant inner product. But actually, I don't like this system. One reason, very simple, which is the energy eigenvalues may be complex. It can be anything, actually. That means the energy is not observable. We cannot observe a complex number, or it's not easy to observe complex number. Secondly, I don't like it is for this system to have this unitary interpretation or unitary formalism, it's necessary to have 2 evolution equations. One is for the right state, one is for the left state. And they have a different evolution operator. One is a Hermit conjugate to each other. That leads to the 2 types of states. One is the right, the cats, another one is broad, the left states. And they are related, but not equivalent. And you cannot take a Hermit conjugate easily to convert one to another. So that means if give you a state without saying there is ambiguous whether it's a left or right state. And more severely or more, I think it's the one of the problem or one of the drawback shortcoming of this formalism is the naive definition of geometric face is complex, which is Garrison Wright first introduced this face in maybe 1990 or 1988. And that face is basically using left and right, and the dot is only on the right. And this is, you can very quickly to verify, this is in general a complex number. If it's complex, it's harder to interpret why it's a face. Well, that's the first set of formalism. Second is a PT symmetric quantum mechanics. And here P is parity, which is evolution, P squared equal to 1. Time reversal is also involution, T squared equal to 1. And also antilinear. There are two choices for time reversal. It could be complex conjugate or also together with Hermit conjugate, which means together with transpose. I will mostly using the second one because it's just simply easier to manipulate. Okay, here there's a question in chat. Why don't you like energy complex classical equation of motion can also have? Yes, classical one, yes, but the quantum mechanical one, you cannot observe a complex energy number. In classical, everything is observable. And so it is, there is, well, let's put this way. I just personally don't like it. Okay, I'm not saying it's wrong or it's not useful.
I have a question.
Yes.
I'm not happy with your definition of this A star. What do you mean by complex conjugate of an operator?
Okay, for simplicity, in this talk, I'm limiting to finite dimensional system. Then complex is just every matrix element being taken complex conjugate.
And so, well, you're fixing a basis. That's the point.
Yes, that's right. I'm fixing a basis. Otherwise, I have to define properly what that dagger means. Here, so, non-Hermitian is giving a basis. When I write a matrix, if it's apparent, the most naive non-Hermitian, I will call it non-Hermitian.
But then how do you choose that basis?
Well, in my talk, it's given.
Okay.
Maybe Qing-hai means that for any basis, there should exist an operator T that connects A with A star. Now, I think you can't make that claim. I don't think that any given A in any given basis can always be related to A star by an equation T equals A star.
Well, this is a finite dimensional system.
I'm not even sure it's correct for finite dimensional. But
well, let's put it this way. Mostly I'm using the latter one because it's more convenient to manipulate. But some examples, of course, you can easily construct this, the early one. If it's complex symmetric, then it doesn't matter.
Okay.
Okay. Yeah, I'm not really dig very deep about these definitions and do it very carefully. My purpose is to try to reinterpret it. Okay, and Hamiltonian to be a PT symmetric here means PH dagger P equal to H. If using the star as a complex conjugate, then this dagger replaced by star. The eigenvalues of this HBT are either real or form complex conjugate pairs. If it's diagonalizable and all eigenvalues are real, we call it PT symmetry is unbroken, and otherwise it will be broken. If it's unbroken, we can restore the unitarity by introducing the metric operator, which is a C operator, related with C operator, which is a PC in this definition of T. I think there's another question. Oh, okay.
I just want to line out, if you want to have a correspondence principle, which is only also valid in the complex plane, you need to have complex energies.
I do not have that yet. No.
And the other thing is, if
actually,
you have
in this talk, I'm focused on finite system. It don't even have X.
Well, if you want to have causality and anti-causality, you have two boundary conditions. So you have a non-Hermitian system in the PT broken phase.
Well, that may be the future work, but in this talk, I will do a simple matrix, mostly 2 by 2.
Well, that holds also for matrices.
Okay. So there are examples about time-independent PT symmetric system. The most famous one is Bender-Boecher potential. We are too familiar with this spectrums. There are broken regime and unbroken regime. Another example, which is the experimental realization, which is so-called passive. Passive. I think there is a. Let me just admit to. Okay, there is a passive PT symmetry, which been first realized or simulated using optical system. Okay, here I'm going to say a few more words about this metric operator. For any PT symmetric Hamiltonian with unbroken PT symmetry, we can define a new inner product, which is with a W inside. That's why it's called a metric. This W is a Hermitian in the direct sense and positive definite. All the eigenvalues are positive, cannot be 0. HPT is actually Hermitian under this new inner product. I know there is a definition, subtle difference between Hermitian and self-adjoinness, but here I'm considering finite system, so there's no difference between the two. So this is the Hermitian most mathematician, or actually they call it symmetry, more familiar with. So in the sense, if PT symmetry, PT symmetric Hamiltonian with unbroken PT symmetry, it is a Hermitian in disguise. And unitarity can be restored with respect to this new inner product. Introducing W helped me to formulate time-dependent PT symmetric quantum mechanics. In this case, I'm not using a bi-orthonormal basis. I'm using a single base system. So therefore, the bra state is simply the Hermite conjugate of the cat state. And secondly, here I'm allowed the metric operator to be time dependent. So W may be T dependent because Hamiltonian itself is T dependent. In this case, the unitarity simply means the inner product with W as a function of T altogether. Everything is a function of T, but the inner product it's not. Well, the solution, the price I have to pay is we have to modify the Schrodinger equation because the naive Schrodinger equation doesn't allow these 3 constraints, particularly it doesn't allow the unitarity. So if we change the Schrodinger equation, not only with PT symmetric Hamiltonian, but also with additional term, which is the only depend on the metric operator, then we can have unitarity, real spectrum, which is only the HPT part of the real spectrum. And we can easily construct a real geometrical phase, which for Barry phase, it will have this simple form. Okay. In our paper, we didn't realize we can write this as a simple form we using two terms, but actually can be simplified into one term. But there is a severe drawback, which is for all this to work, we need W to exist, and for W to exist, we need unbroken symmetry. So therefore, even though your Hamiltonian is PT symmetric, time dependent, we cannot allow Hamiltonian to be changed into or crossing from unbroken to broken regime, because at that moment, W stop existing and all these nice features are gone. We cannot have a geometry phase. Well, these together, I can introduce a new framework to do the job, basically like a reverse engineer. So let's consider any non-Hermitian Hamiltonian, or we just call it time evolution operator. We do not consider it as a observable, energy observable, normally called Hamiltonian. So we can either call it effective Hamiltonian or time evolution operator, which govern the evolution of the state in the Schrodinger, the conventional Schrodinger equation type. But here we're asking a reverse question. So this is a given, which is non-Hermitian, not PT symmetric, and doesn't even have a real eigenvalues and no complex conjugate pairs. But it has a evolution was governed by it as a Schrodinger equation. And now the question is, can we find a metric operator such that under that new metric operator, the inner product governed by effective Hamiltonian H effective to have unitary interpretation or unitary inner product? Well, this turned out to be not hard. It actually can be done. As long as W satisfies this first order matrix differential equation. And then we can, using such a W, there are no initial condition involved. The initial condition actually is arbitrary as long as it's positive definite. And then we can find W such that together H effective and W, we can form a PT symmetric system with unbroken PT symmetry, just like I did in the previous part. That is, we integrate any time evolution to be two-part. PT symmetric part, we call it Hamiltonian, which have real eigenvalues, and the anti-PT symmetric part, which actually related with the W. Because of I, so make it anti-PT symmetric. K itself is PT symmetric. We can immediately, the K part actually can be immediately calculated based on this equation. K must be W inverse times W dot times -1/2. And it turns out W can be solved by by decomposing W or taking square root. W, since W is positive definite, you can always write it as eta dagger eta. And eta is arbitrary, as long as no zero eigenvalues. So as long as non-zero, it can be complex eigenvalues, that's fine. So, and eta satisfy a simple Schrodinger-like equation. Here, eta is not a state, it's an operator. If it's 2x2 system, two-dimensional system, this is 2x2. But it satisfies a very similar Schrodinger system, but it's like a left state instead of right. But it's not really a state. So that means for this equation, obviously any H effective under very loose constraint, which is related with time ordering, related with whether it's diagonalizable, but it's not the moment instantaneous diagonalizable, but it's after you do the integration with the time ordering. But well, let's put this way, a generic effective Hamiltonian, this is the first order equation, we can always solve it. And this is basically the solutions can be constructed by flow case theorem. And the better yet, the initial condition is arbitrary because the W satisfies only the equation, not boundary condition. As long as there are no eigenvalue, no zero eigenvalues, this is fine. Different choice of eta zero corresponding to different W, but actually they are related, they are equivalent. Okay. So therefore, if we give you H effective, we cancel the anti-PT symmetric part, we left with the PT symmetric part, and with unbroken PT symmetry by construction. So in this way, we reinterpret we reinterpret the non-Hermitian system. Non-Hermitian is simply, generic non-Hermitian is the summation of a PT symmetric plus anti-PT symmetric. And that partition is unique. There is a question, is ansatz for the Hamiltonian operator consist of Land-Blood equation? I'm not sure, but I think our system is simpler than Land-Blood equation. I could be wrong. I'm not very familiar with this. I only listen talk about the Land-Blood equations. But I think our system is probably not equivalent. Whether it's consistent, I don't know. I think it's not equivalent, but maybe consistent. Or I believe our system is simpler. So let me reiterate. Give you any non-Hermitian Hamiltonian or matrix, you can always, in the matrix case, it's very easy to separate the matrix to be a Hermitian part and anti-Hermitian part. Any matrix can do this separation partition, and that's unique. Actually, you can also do this for PT symmetry. You can always, for any given matrix, you can do a PT symmetric part, which is set by this equation, and anti-PT symmetric parts. And that partition is also unique given H and W. So it's like generalization of Hermitian, non-Hermitian partition of any arbitrary matrix. At least for finite system, that's simple, can be proved. We have done that a while ago. So therefore, if any non-Hermitian system actually has a built-in PT symmetry with unbroken PT symmetry, and then it would be a natural question is, let's apply this interpretation into the non-PT symmetric system. For example, what if my effective Hamiltonian, it happened to be PT symmetric already, HPT, and it's not even depend on time, simple one. Okay, for this case, there are two possibilities. One is the PT symmetry is not broken. If PT symmetry is not broken, HPT itself is diagonalizable and all eigenvalues are real. And here I can show you there's another property for unbroken PT symmetry, which is if I'm using this system to interpret, W can be chosen as time independent. And K is W inverse W dot. If W is time independent, then K is 0, then H effective equal to HPT. That's actually as expected. If it's a PT, H is already PT symmetric with unbroken PT symmetry, then better not touch it at all. And it can be done. Yes.
Can I ask you a question?
Sure.
Do you discard the broken regime here?
No. Okay, I'm going to the broken regime. Thank you.
Okay.
In the broken regime, I'm saying all non-Hermitian are PT symmetric, including the broken ones. And then what does that mean? Okay, and I'm going to show you in that case, the broken PT, broken time independent Hamiltonian with the broken PT can be reinterpreted as time dependent non-broken PT symmetry.
I have a question, if I may.
Yes.
What you're doing is potentially interesting and also potentially questionable. If you want to have a Hamiltonian, which is real plus I times this K, then you would expect it to appear in the action. That means that somehow W is already defined before you set up the variational problem, which in a sense is good and in a sense is mystifying. But it seems to me that might be an interesting thing to explore.
Yes, I will not go to operation principle, of course. I didn't define action, but I will, in my next part, when I introducing AA phase, I show you example how the freedom of W can be chosen. That may be, let me show you, maybe have some linked with the question you just asked. So basically, when we have a Hamiltonian, whether we already have a W defined, predefined already. Okay, that I think in this talk, I'm leave that open. I'm just, somebody throw me a 2x2 Hamiltonian like this one on the screen, which is apparent non-Hermitian, and it's PT symmetric, and depending on alpha is less than 1 or greater than 1, alpha is real, and then it's has an unbroken PT symmetry or broken PT symmetry. Okay. All right. Another question? Okay. Oops.
Yes, I actually have a question. I mean,
yes.
One in conventional there's a problem with conventional PT symmetry, and that is that the broken regime and the unbroken regime are really very independent of one another, in the sense that you can't start in the unbroken regime and do an analytic continuation to the broken regime and analytically continue everything, because there are questions about how you analytically continue the metric. Okay, yes. That's very difficult.
Yes. Okay, here the solution I'm going to show you is either inside unbroken or broken, not crossing. I haven't figured out how to do the crossing yet. I don't probably there's no solution to do that.
Right. Yeah. I mean, that's a very difficult problem, because it's very important physically to understand the broken PT regime, and to find a physical interpretation for it. And one would think one could rely on analytic continuation from a regime that you do understand, like the unbroken regime. But maybe what you're offering us is some sort of pathway to go from the unbroken regime to the broken regime, but I'm not sure.
Right. The solution I present today is doesn't do the crossing, but of course it's worth exploring whether my formalism can have some hints about crossing the boundary.
Right, I understand.
We have a lot of solutions. They actually cross quite smoothly from the broken to the unbroken regime and vice versa. But they behave qualitatively quite differently. So usually a sine function becomes an hyperbolic function, etc. But you can cross over.
That's actually,
and that's
the
very
one I'm
interesting,
going to show you.
Considering physical quantities like entropy, etc. They have really different behavior.
That's right. That's right.
In response to Carl, it might be equivalent to a ferromagnet, where you stick on an external field and you find that the free energy is a multiple valued function of the external field. And I think that somehow you break the PT symmetry by adding on a source term and then look for analyticity in the source.
Philip, I think what you're saying is very interesting. And in general, this is a generic question. How do you analytically continue through a phase change? Okay, if you have a system that exists in two possible phases and there's a phase transition, how do you get from one to the other? And it may be a natural boundary. There may be a way of doing it. I mean, certainly introducing an external source is one possible route.
Okay, so let's go back to my simpler finite system. So no variation principle, no entropy yet. Okay, for this system, if it's with a unbroken PT symmetry, it's very simple. And as expected, that Hamiltonian itself, effective Hamiltonian, it is the PT symmetric one, and we don't need that K term, I call it gauge term at all. Well, here actually we can choose this. This is not a unique choice because W is not uniquely determined. But the point is the metric can be chosen as time independent, such that, well, then the K will be equal to 0. And one simple solution will be simply like this. W equal to 1 over sine, and that is Hermitian. And when alpha is less than 1, theta is real. So therefore, it's defined by the trigonometric. So therefore, this W is well defined. And you can see the problem when alpha approaching to 1, then theta is approaching to 0, then there will be a scaling problem occurs. In this case, H 2 by 2, it is a Hermitian under this new inner product. And the unitaries can be restored by using this W. So that's essentially the C operator or PC, Carl and Dodgy and Hugh Jones a long time ago calculated. It's more interesting to do it with a broken phase. In the broken regime, energy is complex. Now, at this time, I reparameterize, just like Andreas correctly mentioned, by hyperbolic instead of trigonometric. In this case, the metric operator, I can solve a metric operator. This is one solution. And the problem is all the solutions, W must depend on time, cannot be time independent. And which the reason is obvious. If W is time independent, K must be 0, and then H has to be unbroken PT symmetric. And we know H is not unbroken PT symmetric, it's broken. But for this particular choice of W, you can see the red ink T dependence. And then in this case, the effective Hamiltonian turns out to be only the gauge term. There are no PT parts, happen to be. Well, this is of course because this model is very simple. That means for this very simple model, when you inside the broken regime, it's a secretly time-dependent unbroken PT symmetry with a trivial PT symmetric Hamiltonian, which is 0, 0, 0, 0. But with a non-trivial metric operator, which is this. And that will give you all the evolution which that unbroken, the broken PT symmetry Hamiltonian gave you. If the original PT symmetric Hamiltonian is time dependent, then in general, of course, W will be in general time dependent. Then what is the PT symmetry or non-PT symmetry actually means? And here is a subtle issue, which is the instantaneous symmetry breaking doesn't mean anything. Because we know the evolution does not follow the instantaneous eigenstate. Even for very slow evolution, the adiabatic following, it may not be achievable. There are several papers, I wrote one too, to show non-Hermitian evolution may not have adiabatic following, no matter how slow the evolution is. The first one is by Stefan Roth. And therefore, that also means the instantaneous energy eigenvalue or eigenstates doesn't mean much because the evolution dynamic doesn't follow it. If we consider a special class of this time-independent system, namely periodic ones, for a periodic system, there is a distinction, which is whether the system has a long-term stability. I call this extended unitarity, and Jugic Joglecker call it unbroken Floquet PT symmetry. probably the latter one is more mathematical accurate. Which means for periodic system, if you have a long-term symmetry, that means after one period, because of Foucault theorem, after one period, it cannot evolve into a crazy state. It has to come back to its original norm. Then that's how after each period, you don't blow up. If after one period, a scale by factor of 2, then after 2 period will be factor of 4, then eventually blows up. So therefore, for long-term stability, it's necessary to have, this means the Foucault operator, the time unitary, well, U of t, not unitary, but time evolution operator in this case, must have a real phase, must be unitary in the normal sense. Okay, in this case, it's an equivalent of unbroken PT symmetry, but not on the instantaneous eigenvalue case. In this case, we found W actually can be chosen with the same periodicity. So W is also periodic. If it's in the broken one, which means you do not have long-term stability, then W cannot have the same periodicity. So therefore, even your Hamiltonian come back after one period, but W necessarily doesn't come back, then of course you do not have a cyclic system. Your inner product doesn't come back, then you cannot do this broken. You cannot do this. Well, it's harder to introduce in geometric phase. Okay, that's the using this new framework to reinterpret a non-Hermitian system. I'm going to show you one examples, which is AA phase. In PT symmetric system, if we have a periodic system, oops, and with unbroken PT symmetry itself, so we'll leave the broken one later, and then W can be chosen, have the same periodicity. In this case, we can consider a cyclic state. Well, the W to be periodic has a great advantage. That's how the inner product can come back. Otherwise, even though the state may be cyclic, but the inner product doesn't, then we still don't have the same Hilbert space back. For any cyclic state, which is after one period is only develop a phase, which is possibly complex phase, since it's non-Hermitian. And for this phase, we can part it into two parts. One is called dynamical phase, which is can be defined by the PD symmetric part of this H effective, not this H effective, the PD symmetric part of it. Another one is the geometric phase. Oh, sorry, this is H effective itself is PD symmetric. So this H should be the same. Sorry, it's a typo. And the geometric phase, which I showed you earlier. This geometric phase can be proved to be real and gauge invariant. Here, gauge means if you do an arbitrary function with multiply the state by arbitrary phase, which is can be a function of time, then this geometry phase remain the same. Well, we can, since that is a PT symmetric with unbroken PT symmetry, now let's consider a more generic case, which is just giving you a cyclic state, okay? And we can define a AA phase with respect to an arbitrary periodic metric operator. It's a metric operator, so therefore it's a Hermitian and positive definite. And here, for simplicity, we pick it to be periodic with the same periodicity as the cyclic state. That is, if you give me one state, I can either give me a W, then I can define, or I can use a W to define geometry phase. And here the definition of this geometry phase. This phase is real and gauge invariant. If we choose W to be simply 1, and then we actually recovering the geometry phase I proposed a couple of years earlier, which is generic. If W is not 1, then we'll have different ones. Okay. Here is the interpretation or understanding what these two ugly terms means. The first term, it looks like the total phase, but only taking the real part of it. Because you can see the inside the logarithmic, the numerator is complex conjugate of the denominator. So therefore log of it, it will be purely imaginary, and multiplied by minus I, it becomes purely real. So that's actually only real part of that. We can call that total phase, which means we ignore the scaling or the scaling being canceled out, only focus on the phase part. And the second part is dynamical phase. Since I call that total phase, this is geometry, so this should be interpreted as a dynamical. Well, the cyclic state is arbitrary, but if it happen to be this state satisfy a non-Hermitian Schrodinger equation, and you can, by simple manipulation, you can see this dynamical phase turns out to be with this form. That means any anti-Hermitian or anti-PT symmetric part of H effective will be dropped out. Only PT symmetric, here PT respect to W. So W symmetric part contribute to the dynamic phase, and that's why it's real. Well, the real can be proved here, obviously. You can see the numerator is Hermite conjugate to each other with a minus sign, multi-side, that's real. But here, now we understand why it's real, because this is only counting the unbroken PT symmetric Hamiltonian, that dynamic evolution, and that is real. We can decompose respect to W. We can always decompose H effective into Hermitian PT symmetric part, anti-PT symmetric part. In general, that anti-PT symmetric part is not W inverse W dot. In that case, in general, the unitarity is not there. But if happen to be K equal to W inverse W dot with minus half, and then we recover PT quantum mechanics here in time-dependent quantum mechanics. If the cyclic state, you may wonder how can we construct a W, or what it's a W is a good one. If a cyclic state belongs to a complete set, and here complete means I complete every moment, always complete. So there are no crossing, no correlates between the states. In this case, W can be simply constructed by this. And here n is arbitrary real positive numbers. Different choice of n corresponding to equivalent but different W. So that is, I can define a generic general AA phase for any cyclic state respect to any arbitrary pure periodic metric orbit. And this one also can be generalized even into a non-cyclic state. That means the state evolve doesn't come back. It just evolve from A to B. And then we can define a, well, that's difficult is how to define a total phase, because it doesn't come back, so we cannot easily define. But if we define that thing like that, this is actually in the spirit of paracharotinum phase. And when we define that, assuming the denominator number goes to 0 at any moment, and then we can define a very similar dynamical phase like before. We can define the geometry phase. And this geometry phase has a simple interpretation if W equal to 1. And this interpretation is simply, and also in 2 by 2, this simply means we have an evolution does not close because it's not cyclic, but if you close the two end by geodesic, and then we have a circle, and that circle some solid angle, and that solid angle is this geometry phase. So that is just like a Hermitian one. Okay, I think I better summarize. I conclude. All actually here all means finite dimensional and probably either diagonalizable all at the end after the time evolution is diagonalizable. The question is, if W is ambiguous at the choice of number n, does this mean the phase are ambiguous? Yes, the phase is the subject or the consequence of the state and metric. So this is come back to Philip's earlier question, whether when we have a Hamiltonian, when we have a state, whether we already have a metric operator defined. I think most mathematicians will take the latter view, which is when you have a state, you already define the metric. And here I make that freedom, arbitrary choosing the metric. PT symmetry breaking has a new meaning, which means the metric operator become time dependent. Unbroken can be time independent, but broken must be time dependent. So that's also why the PT symmetry breaking is so dramatic. It is some quantity suddenly become changing in time. For K, PT symmetry breaking changes the periodicity of WT. Since W is already time dependent, but it become the different periodicity changes in the flow K, which is a time dependent case. Many time-dependent PT symmetric quantum mechanics application can be extended to generically non-Hermitian system like Jarzensky inequality, Crookes fluctuation theorem, Berry phase, A phase. I already showed the A phase, quantum geometric tensor, which is also fascinating. We wrote 2 papers on that. All time-dependent PT symmetric system has a geometric structure. This is quantum geometric tensor. This tensor has 2 parts. The imaginary parts gave Berry curvature, and the real parts induce a metric tensor in the system parameter manifold, that different metric. So this terminology is borrowed from Hermitian quantum mechanics. In that case, the quantum geometric tensor serve these 2 purposes. And we can extend that to PT quantum mechanics. Now we can extend that using this new interpretation, extend that to generic non-Hermitian, because all non-Hermitian are PT symmetric. Okay, I will stop here. Thank you for your attention. Any questions?
I know many 2x2 matrices which are PT symmetric, and they have in the unbroken and broken phase time independent metric. The only difference is that the metric is different in the 2 phases. So what you say is PT symmetry breaking has a new meaning to give a metric operator time dependence.
Right. If we want to, if we want to reinterpret that broken one as a time-dependent PT symmetric system with unbroken PT symmetry, then W must be dependent on time.
It seems that, unless I misunderstood, it seems you have something very general here. Namely, you introduce a W and it's either time independent or time dependent. And those 2 choices correspond to 2 different realizations of PT symmetry.
Yes, but there's a slight subtlety, which is in the unbroken case, I can still choose W to be time dependent, but it doesn't tell us any new information.
Okay, so if
because W is the solution of an evolution. Let me go.
Okay.
Here, W is the solution to this equation. So even H effective is not time dependent. There's no guarantee the solution is not.
Yes. Well,
that depends on your initial conditions.
Oh, that's a different point.
Yeah, okay. Because we're integrating one time. So integration after integration may or may not be time dependent. So eta t is time dependent, but eta dagger eta may or may not be time dependent.
Yes. So
If I
my earlier question about putting W into the action really boils down to putting eta into the action.
Yes. Well, yes.
Eta seems to be the more central function rather than W itself. Now, the other thing that I asked this a little bit before, but I'm still puzzled. If you have an evolution operator with the K, then for that evolution operator has to obey Poincare invariance in the final analysis. And that's why I think, I mean, you've got an operator that generates ID by dt. Is it the generator of time translations? And if it is the generator of time translations to begin with, then there must be an action formulation where you can see the Poincare invariance emerge. I mean, I understand you're doing non-relativistic, but nonetheless,
Right.
you still want you still want some object to be the generator of time translations. And it doesn't have to, if you're saying is if it's h minus I over 2 w to minus 1 w dot, some object, somehow that object has to be in an action. And it has to be the Legendre transform of the Lagrangian. If it isn't, then something major changes in the way we formulate.
Well, I think, of course, I don't know the answer to your question, but there is a subtlety or dangerous part to venture in that direction, which is the C operator, like W is PC, W basically is C operator. And like Carl and the collaborator already shows in the infinite dimensional system, like with X, then W may be LD, maybe itself may not be bounded, maybe unbounded. If W is unbounded, my system is done because I have W inverse here.
Yes. So
the question is whether we can have a unbounded W, and that if it's always unbounded, then that simply means my formalism does not work for infinite dimensional system, only finite system.
But K,
it could well be. I think it could well be in that direction.
But K could still be bounded, even if W isn't. K is W to minus 1 W dot.
That would be, yes, it's possible, but that would be too hard to manipulate. I'm manipulating W, just as you said, it's actually really it's eta.
Yes.
So if eta unbounded means eta has a infinite eigenvalues. All the eigenvalues goes to infinity and goes to 0, then there will be an issue. Actually, even in the finite system, there is something I hidden here, which is I said any system, non-Hermitian, stable or not, I can do reinterpret as unbroken PT symmetry. But there is actually all this interpretation only valid for a finite period of time if the system inherently unstable. If the system is stable, and then my interpretation lasts forever. But if the system is unstable, like the broken PT symmetry without time dependent, is obviously unstable. It's exponential growth or exponential decay. In that case, I can always choosing W with this right arbitrary chosen numbers. So I can, in another way of saying, give me a finite period of time, I can do the job for you. But my formula eventually fails when the time running too long, because the system is, if it's unstable system, I cannot render it stable. I just hide it inside W, but that hiding eventually break down if it's too unbounded. So that's causing W to be not well behaved.
Okay, I mean, all I can say is that if you are able somehow to relate the C operator to time translation invariance, I think that puts the C operator on a rather strong theoretical footing. I mean, it would be a whole new role for it. And I think that would be extraordinary.
I hope so, but probably long term. I think Sajid Sarkar has raised his hand. I better answer his question. Yes, Sajid, do you want to? Oh, you have typed, please provide us the reference of your talk. Oh, okay. The reference, they are few. Let me see, did I put it? Okay, that is one reference. This is the, oh, this is not extremely relevant. Here, the most relevant reference is this. We published on PRA 2019, which is using PT symmetry to reinterpret non-Hermitian. And there are also all the other previous work being cited there. So this is the most relevant, the majority part of today's talk. And for the AA phase part, the generalization one is the new work, the new work thanks to the COVID lockdown. That's during the lockdown. That's my work. We call it circuit breaker in Singapore, and that only lasts for 2 months. After that, I have to teach, and I didn't do anything afterwards. So I wish the lockdown come back. No, I didn't wish that, but that's a way to improve productivity.
Just a comment. My experience with 2x2 Hamiltonians is that the metric is related to the diagonalization process. So to the matrix, which of the eigenvalues, the left or the right eigenvalues. And this is not ambiguous. So this is why usually the matrix depends on these normalizations of these matrices of the left or right eigenvalues. But what you are doing is somehow looking at the anti-Hermitian part of your Hamilton operator. And this is related to the diagonalization somehow, or to the diagonalization of the imaginary parts of the eigenvalues. So you have not a really complete diagonalization of your Hamilton operator. So that what you call W, I would not call in a sense a metric, because it doesn't affect the whole properties of the metric. And this may be the reason why you have this pop-up of a time dependence, while I obtain time-independent metrics even for arbitrary PT symmetric matrices. The only thing I know is that in the broken and in the unbroken phase, these matrices are different, but they are not ambiguous because they depend on these normalizations of these left and right eigenvalues. Another thing what I wanted
do not
to say
have
is,
but sorry to interrupt, I do not have a left and right.
Yeah, well, you come in with W, and then you go to the Hamilton operator, but you can go the other way around. Sorry, my background here is a bit
That's
loud.
okay, but the problem is how many
the other way, and then you obtain ambiguity, and you are tackling somehow the imaginary parts of the eigenvalue.
I disagree. The key difference between left and right is you require to have 2 evolution equations. I only have 1. Although my one is a complicated one, but I only have 1.
This I take into account in my derivation of the metric, and these matrices which contains the left eigenvalues and the right eigenvalues, they are mutually inverse to each other, but they are not necessarily unitary. But what you are looking at is the anti-Hermitian part of your Hamilton operator, and there you somehow have only part of your features of the whole Hamilton operator. And this creates a time independence which doesn't appear in my way of determining matrices, because matrices, because they, in my case, they are all time independent. They are just depending on the parameters of the Hamilton operator.
Apparently, we're doing in 2 different ways.
Yes, but I'm very surprised that you have this feature in that you, in the broken phase, obtain time dependence. This means there's something in your matrix which is not really a matrix. Yeah, as I myself looked into that.
I guess we have a definition for matrix differently. Matrix, what is the definition of matrix operator differently?
Yeah, well, you set up a matrix element in order to obtain something which is constant, yeah, and then you made
yes,
constraints.
That's my definition.
Equations of that, yeah. But I think by posing your constraints on these matrix elements, I think you fix something which usually should not be fixed if you want to have a correspondence principle. My opinion,
I do not have correspondence principle.
You started with Neumann-like equations, and they are somehow determining the density matrix. And you set up a scalar product or inner product, which somehow defines a quantum theory. Yeah? But my opinion is, in the same way as you have a correspondence principle for classical equations of motions, which can be extended in the complex plane, and you need not to have real observables. The same happens to matrix quantum mechanics. You need not to have real observables, you can have complex observables. And by sticking to this idea of real observables, you pop up something which usually in a general setting where you somehow allow complex observables will not be this case. The other thing I wanted to comment is there is a system where there's popping up in quantum field theory PT symmetry breaking when you solve Bethe-Salpeter equations and you have a bound state and you come to the point where the binding energy goes to 0 or something, then you get Bethe-Salpeter ghosts, and the equations, they automatically create PT symmetry breaking, even without referring to any matrix. It's just a matter metric itself of a metric you system agree to Carl that he says these transitions from not breaking PT symmetry to breaking PT symmetry, it's not a simple analytic continuation, because the metric in the broken phase and the unbroken phase are distinct.
Okay, thank you for your comment.
Okay, any more questions?
If I can make a comment on Frida's comment, in purely classical physics, you can take Poisson brackets and you can continue them into the complex plane by a complex symplectic transformation, and that's just as good a representation of the classical mechanics as the real one. However, it's devoid of content, unless when you do that continuation, you cross the Stokes line. If you do, then on the other side of the Stokes line, that's a whole different branch of classical mechanics. And it's the one for which you will get the correspondence principle into quantum commutators, which are in the PT phase. So to say the classical mechanics can be formulated with complex numbers, I completely agree. But the question is, does it have any content? And
I disagree, because I constructed a correspondence principle which gives for arbitrary complex observables in quantum mechanics in the limit of classical systems, the classical equations of motions in the result. So but the only thing one has to stick to, and
what you've done, I think, is you've got a set of Poisson brackets which cannot, by a symplectic transformation, be brought to real Poisson brackets.
But what you see in my
That's
chat
okay, that's
is
what I'm saying,
that
that's a whole different-
I say this is a general distinct system. Either you have PT symmetry breaking or you have not PT symmetry breaking. In one case, I consider the system causal and anti-causal and local, and in the other, I consider it acausal and non-local. So these systems are different from each other. And this is what you say, in other words.
Ranjit has a question. Ranjit, you want to ask your question?
Ranjit.
Am I audible?
Yes.
Yes.
Okay, thank you for the talk. I think I have not fully understood what it is exactly you are doing, but it seems to me some things that appear here, I have seen them elsewhere in other papers. I am yet to read your papers. Firstly, for example, the breaking, the factoring the metric operator W into eta and eta inverse. That is in some sense there in Ali Mustafazade's 2010 pseudo-Hermitian paper, a big review paper. So
yes, of course. That's why I call it ETA. I follow Alice.
Yes, it's also there in. I did some search before because I was working on it. Even Freeman Dyson used it elsewhere long back. This kind of a factorization. And then, if I remember correct, I vaguely remember Mustafazadeh in passing makes some comment. Maybe it's Mustafazadeh, or maybe it is Sarah Crook's 2015 paper, or maybe it is Franco Nori, Adam Mironovic's last year paper. They make a comment in passing that in general you are always have some complicated metric operator in a diagonalizable basis, but they are complicated, they are time dependent. So that looks a bit familiar. I'm not really well read on going into the PT symmetry broken regimes. So skipping that part, and then when you have this kind of equation K, which is factored as W inverse W dot, you write an equation of motion for states. Whereas, for example, how Mironovic and Franco Nori have done in last year's paper, if you...
I have done this 10 years ago in 2010.
Probably true. I'm sorry, I haven't read it yet.
I believe if you want to go through history, the history, I think, is this. I think most people believe metric operator must be time independent, otherwise there is a difficulty to define the Hilbert space. And they probably right from a mathematical point of view. And I am the first to saying, okay, what if W is dependent on time, and what if we want unitarity, what can we have? That's my 2010 paper.
I think we wrote a paper in 2006 pointing out the difficulty.
Yes.
And Heineck Bila wrote the paper with a solution which is consistent in 2009.
By the way, the notation went back to Gaia, and he called this eta rho. This was even before.
No, that was not time-dependent, Frieda. That is incorrect. That is incorrect.
No,
we're talking about the time-dependent metric.
But the letter rho,
that is incorrect, Frieda. That's incorrect.
Eta goes back even before Gaia.
No. We are talking about the time-dependent metric. That's really quite different.
Well, in 2003, I wrote a paper about quantum cosmology, where the metric is time-dependent, and you can find some of the equations there. It's classical quantum gravity paper, 2003. That's the oldest thing I know.
I mean, the term looks like, I think what Ranjit said before, the additional term looks, of course, like a gauge term. Yeah, that goes even further back. But the key is this is not a gauge transformation, right? But formally, it looks exactly the same. So the equations are well known for many, many, many years. You know? But maybe we should stop it here and not get too much hooked up on history. Yeah. So.
Yes, I agree. Continuing the second part of what I was trying to say, these three equations, especially K is W inverse W dot, and H total is H effective plus an anti-Hermitian kind of term. If you do a density matrix treatment, and if you take any Lindblad equation, for example, in any systems, not necessarily a non-Hermitian or PT-symmetric system, and neglect the jump term, essentially the total Lindblad equation is you have this commutator part, which is Hermitian part, and then you have what is called as the Lindblad part. The Lindblad part itself has can be seen as a combination of two things. One is an anti-commutator part, and another one is what is usually called as jump part. Now, if you neglect some jump terms and observe the remaining corresponding anti-commutator part, you can recast the Lindblad equation when the jump term is neglected in exactly this manner. That is also in some sense seen in some literature I have been referring to. Somebody asked a question about if this is consistent with the Lindblad treatment. So that's my answer. It is, but there is a way to see it. It is exactly equivalent to Lindblad treatment with jump term neglected. Okay, that's all I wanted to say.
It says that the Lindblad is more general.
Okay, shall we stop here? Yeah. So let's thank Qing-hai again for a nice talk. Yeah, thank you.
You're welcome. Thank you for listening.
Okay, I'll see everybody when I have a chance.
Have a good break, a nice Christmas to everybody. 14th of January, we continue. Yeah.
Andreas,
stay healthy.
Thank you, Andreas.
Corona
Andreas, the link.
Christmas days.
The link that you sent us. The link that you sent us for the proceedings is now in the chat. Could you send it again?
It's on the website. It's if you go to the conference website, it's over there. It's from the conference website.
Okay, I hope to find it.
Yeah.
All right, everybody. Well.
Thank you. Qing-hai, may we ask you the slides, please?
Oh, sure. Sure.
Thank you
I can send you the slides.
Yes. Thank you.
Good to see you, Qing-hai.
Okay, thank you.
And say hi to Rum.